Hi everyone, and thank you for joining today's webinar on the PSS Sincal version 15.0 release. Today my colleague will be giving you an overview of select new features in the latest version. My name is Danelle DeSormo and I will be the moderator for today's webinar. Now, before we get started, I would like to go over just a couple housekeeping items. You're able to ask questions throughout the webinar. To do so, please type them into the question box in the GoToWebinar control panel, which is located on the right-hand side of your screen. We will also have about 15 minutes at the end of the webinar for questions and answers. So if you have a question throughout the webinar, please do not hesitate to answer it, or excuse me, to put it into the question feature box. You are also able to download a copy of the presentation materials from the Handouts feature, again on the right-hand side of your screen. Now, before we get started, I would just like to introduce our Siemens speaker for today, Ms. Ulrike Sachs. She's located in Germany and she is the Sincal Products Line Manager. Now, without further ado, I would like to hand it over to Ulrike.
So thank you, Danelle, for your introduction, and welcome also from my side to this webinar. First of all, I want to apologize for my voice because of flu. So this time I want to focus on the 10 main features of the version 15. Other features you will find in the release notes as usual. So to start with, we added SQLite to the supported databases in Sincal. So that means actually we have the Microsoft Access as a standard database, and then for larger applications the Oracle versions and the SQL Server versions, and now we added SQLite. Why should you use SQLite? First of all, it is a public domain library. That means you get it at no cost. It's directly implemented in the software. It gets more performance in the simulation for you, and there will not be any dependencies of DB installations when having a 32 or 64-bit version. So you don't have to care about, do I have an Access 64-bit application when I run a 64-bit Sincal version. Also, it allows more detailed evaluations in the Sincal, and this I will show later on also. In addition to that, you will find a lot of free browsers also in the internet to see into the database, as you may be used also for Access. But to make it very clear, it's a solid desktop application. It's not meant for a complete network. SQLite database systems, why should you use it? We said it allows to use the SQLite database exactly in the same way as the Access, so we implemented it in the same way. In SQLite you have the SQL 92 standard from the complete programming interfaces. You can use different programming language. You can have Python, you can have Java, so it's really open as Access before. It allows also that you have a mixed operation between the different databases. For instance, if you have include networks, one network can be in Access, the other can be in SQLite, or maybe you have your libraries in Access but the network in SQLite. To create a network in SQLite, this is very simple. You switch on the feature in the Access option menu, and then when you do file save as procedure, then you directly get an SQLite version. The second topic is the new tabular view we have in the Sincal, and this allows to efficiently evaluate through all the large data and results you can have in system. It has the same behavior as before, so it handles all input data and all result data in a structured way, but now we have much more filters and sorting functions and also integrated searches. One specific new feature within the tabular view is the new filter line. You see this is this button in the red box here. With this you get a new line, and in this line now you can enter queries like I want to have all voltages lower than 95%, or you can also state things like I want to have all voltages lower than 95% and higher than 105%. So this is now completely open. You have operators, you have and or operations. You can sort according to a specific feature like you want to have it. And you will see there is another option now available in the tabular view. When you move to a specific element or node, and then in the context menu with the right-hand mouse button, you can directly link to the network data itself, or to the results, or to the nodes and branch results as you want to. That's a direct link between the tabular view and all the other tables. We added also a new box. We call it Filter with Browser, Network Browser. That is a nice tool if you have no graphics available and you still want to navigate through the network for evaluation. So you have your network browser, you click on a node, for instance, you get the complete connected topology in the browser, and at the same time you see in the tabular view the input data for that, the results for that, that you can quickly serve and evaluate in the software. And the second or third feature we added in the tabular view was that we added the result compilation in the tabular view. So you get as default the result compilation you did before. So what is the interactive result cockpit? You may know that we added that last version, but now we have it completely also in tabular view. So this allows the user to create a result view interactively. It works throughout all variants and scenarios, and also for all the different calculation methods. It allows filtering and setting of limits, and it's linked to the network direct interactively, and now also embedded to the tabular view. Multidimensional results you can see. That means you can create your own view through the variants for a name or for a branch in the system. You see combined results for load flow and for short circuit, for nodes and for branches. You can color code, for instance, voltages within the limit I want to see in a color, or only loadings which are higher than 95%, and combine that also together. But I guess best is to see it live, and therefore I now just switch over to Sincal to show it in the application. You see the very famous network example 11. I guess everybody from you knows that network. And now we want to first of all define a multiple calculation and then do the result view. I added to this model different variants. You see I have a base case which I actually loaded, and then I have case without a motor added at right side and only one node. That is the first step. Then what I can do is go to calculation, multiple calculations, and now across all the variants, that would be also possible for scenarios, but at the moment for all the variants, I can define I want to run a load flow, and in addition to that I want to run a 3-phase short circuit, 2-phase short circuit, single-phase short circuit at the same time across all the variants. Then I do the simulation. That means Sincal automatically performs all the simulations through the variants in one run. And if it's finished, so then I can get to the result view, switch on the result compilation, and create my result compilation. So on this side I have the available data, and there I move in now the values I want to have. For instance, for the nodes I want to have the name, for the network elements also the name, Okay, then I want to have, for instance, for the load flow node results, I want to have the voltage in percent, and for the branch elements, I want to have the P and the Q and my current. And then from the three-phase short circuit node results, I may want to see my starting short circuit power. Okay, then from the three-phase branch results, I may want to see my starting short circuit current and my peak current, and from the single phase node branch results, I want to see the single phase short circuit current, and from the two-phase branch results, I also want to see the current of the two important phases. And if I am ready as I go, okay, and get a complete overview about my nodes with the elements, I see load flow results, I see short circuit results for branches and for nodes. And now I can go further on. First of all, I can switch on, so File, Variance, switch on Compare Variance. And with this, I get an overview about all variants. Maybe that there are not results for some of the elements because the elements are not in all variants. Now I can also, for instance, sort this result according to the name and also link to the network itself and have the look to all results. That's one option. So we put it aside at the moment. So you see at the moment I did not limit it to elements, so all elements are available. You see the colors here. But for instance, I can now start and say, okay, I want to, where's my filter box? There's my filter box. I want to filter according to the voltage. I want to see only voltages lower than 94%. And also maybe the currents. If the three-phase short circuit currents larger than 4 kiloamps, I also want to see it. And then you see I get reduced data, only 20 out of the 56, and also reduced data also in the system. And when I click on an element, I can directly navigate to this element. I can also have a different look to my compilation. So at the moment I colored by voltages and by currents, but I can switch also on and off directly, can directly toggle the values here. So then you see changes on this side also. Perhaps I don't want to see it like that way, but like that way. So this result view is now also available in the tabular view, exactly as we had it in the result compilation. Okay, I think we should go back to the slides. Next topic is that we added a specific logging functionality. That means you can now in detail see what we do in the background in the simulation. This is important specifically if we do a lot of optimization tasks, like for instance the ICA model, where we have even in a small network more than 500,000 calculations, and you want to know now and do a further evaluation about the different steps. So we added a calculation log where you first of all see what is done, then the time for starting and ending. Perhaps this can take, in this case it takes milliseconds, but maybe, or seconds, but this could also take hours if it is a very large system. Then you see in the log which method we actually are working on, then the algorithm, then the control modes. You see all iteration loops and the times, and this specific logging can be then also filtered and evaluated. So you can say, I don't want to see short circuit, but only the iterations for load flow, for instance. You can also have a different degree of logging. So none means you get it not completely. Low is only the minimum information. Standard means you see problems if you want to do the analysis, and advanced is what you see here. Every step is shown there. This is only available if you are working with SQL database, by the way. If it's empty, please check if you use Access or if you use SQLite. This next is linked to this specific option. We also can now interactively influence the calculation. So you can control if something is not performing like you expect. For instance, load flow is not converging, and now you want to find out why it is like that. So you will get a specific macro menu where you see, okay, it ran through the calculation, and now you can step through and start a new iteration or have a look to the details. So, but I guess this is again something we should have a look to directly. So I switch over to Sincal, close a little bit the result views at the moment. So we start again with the example Ele1. We create a problem manually that we have the option to see this feature. So I open a branch that the load flow will not converge properly. Now when I calculate load flow standard, you will see it runs the first iteration loops. You see iteration 200 has been done. It did not come to an end. Therefore, I could now have a look to the details. So it pops up with my logging. So perhaps I link it a little bit to this side to have more space for other things. And I see, okay, all the nodes. It tends to be okay, but one node has a specific problem. Maybe I want to run 20 further iterations so I can continue. You see, we are actually directly in the simulation. The simulation only stops. It was not finished. So after 50 further iterations, I have a problem still at that bus bar, but it gets better. Maybe I want to see what is there. When I click there, then it zooms into this bus bar and detects, okay, there I have a problem, and then I should fix this to be able to continue with this. Okay, I could also say, okay, take this result as a convergent solution and continue. Then Sincal will stop, and you will see, okay, I have only 33% voltage at that position, but I think it's better to again close the switch, and when we run now the simulation again, you will see everything is fine. So I can close this, and we have 97% at least here at this point again. Okay, then let's go back to the presentation. Next point is a specific feature for the harmonic simulation. Sincal has a lot of features for harmonics, but we added now a feature which comes up more and more specifically also in high voltage systems, or when you want to really evaluate across specific network states. So in general, we run a simulation only for the network state you have on the screen, but sorry, specifically if you have in high voltage systems, for instance, capacitors and capacitor banks which are switched on and off, you want to evaluate through all the different network states, and therefore we offer now a chance that you select the elements which can be in and out and combine them and run through all the states for the harmonics. Of course, that is not very, that then increases very rapidly to different states. For instance, we have only 3 elements. So we have the line, the capacitor with the fixed power, and the capacitor with the variable power. And this now can be even combined. So I have the capacitor and the line and the capacitor with variable power separately, but then the combinations line with capacitor 1, line with capacitor 2, the both capacitors or all the 3 elements. That's still without the controller, but if I then have also different controller taps as a capacitor, 3 taps for instance, then I end up only with these 3 elements to 16 states. So just to give you numbers, when we have 10 capacitors in the system, it's more than 1,000 different states. And that we want to simulate now to find out what are the impedances, the network impedances of the specific nodes for specific frequencies across all the states or for all frequencies. Again, I guess it's better to see it live. Let me go to Sincal. There's a prepared network. You may know this example LA2. It has already the predefinition for the harmonic calculation. So for instance, the nodes I want to have a specific look to. You see these small icons which are showing that. I want to have different network states for there. I have defined a network element group. When I select this group, you see all these colored elements can be in and out and change my network dramatically from the impedance side. Now I want to simulate through all these states, so I go to calculation, harmonics, and then run the frequency scan. With this, I can then select, I want to have only the single connection of the elements one by one, or combinations in all forms. This I want to have at the moment. Consider controller. I'm not sure, I have some on the transformers, maybe we say yes, but at least at the capacitors nothing is on. For the charts, I say at the moment I want to have them individually. I select the group. At the moment I have only one, the network element group with the elements which can be in and out, and then the number of harmonics I want to see between the 5th and the 19th, for instance. Then Sincal runs through all the harmonic simulation, and as a result we are getting 4 specific nodes and 4 specific frequencies. Perhaps there you see the harmonic order. So when I zoom in a little bit, you see now different network states, and then the envelope curve, which defines the complete area where the impedance can be in for this specific node and this frequency. For instance, for the 14th, you see where it is, somewhere here. For the 19th, maybe somewhere here. And the same for other nodes, of course. You see. I also can combine these complete areas, so I can say, okay, combination. Now I want to have combined diagrams and run through again. You see, I have then only the different nodes, but for the complete frequencies, you see the different other network states for the different frequencies and the envelope curves like this. And you can even combine different curves for different nodes in one diagram. So you can use that to find out where you should place filters in this area, or you can also use that to define a resonant network for other evaluations outside of this area. Okay, going back to the slides. Next is more focus now for protection or protection area. We added a specific method for the determination of the fault locations. Up to now we did it directly in the protection devices. Now we have it also linked to the measurement data. That means this element which keeps a linkage to the MDM systems and can read the data directly in a loop. And that means now you can see then the current and the voltage directly from the field in the system updated in a loop. And with this we find out if everything is okay or if we have some fault locator. So maybe we have two different measurement devices, and each of them calculates the fault could be on this line, L3, or on L2. This cannot detect directly if they are there, but only have the impedance. But with the second one, when I calculate the impedance, the fault may be there and there. And if there's an overlap, then I can be pretty sure that my short circuit is something there. I get that also interactively in the result view again. The result view shows me all the different measurement devices which see a fault and where the fault can be. So you have the OD1, which offers two options. So it could be on the element L313 or it could be on the element LMES. These two options I have, and then another relay, another measurement point sees the fault on this list of elements, but there's an overlap exactly at that position, so we can be pretty sure that there is the short circuit. This can now be also embedded, and with this you can then simulate with protection devices directly in the SPI. That is the application where we read the data. That means you can simulate not only based on short circuits you place in the system, but on the measurements. So then the protection device will trip if the measurements have the right currents or voltages. A specific topic in the protection area is also that we added the functionality of reclosers. That means we switched completely the way we do the procedure, the step event evaluation. That means up to now, protection devices which stripped stayed open and will never again close. And now this changed. The protection devices now can open and close. And for this we added to the reclosers a section to the overkind time protection behavior as an area where you see we have 4 different sections. That means 4 different types of detection and tripping, and then you can define the different cycles in each section with the reconnection times and the tripping behavior, and together with the behavior in the network, in the element also with the separate switch on and off times, you can now simulate the reclosers like that. For instance, you have a fault. Sorry, you have a fault. After a delay time, according to the protection device, there will be a switch off time. Then we have the disconnection. Then we will have the waiting time of the reclosers, the switch on time again, and then the protection device switches on again to the network. And this is the first cycle, and then the next cycle comes later. So we can have the different switching operations in the different sections after each other. I guess best is, again, to see it live. Therefore, a small network with a recloser, just a closed loop. So if I have a short circuit somewhere here, the recloser as a single element cannot switch off. We will have a look to the recloser itself. So the definition at the recloser, you see it has now a completely separate individual switch on, switch off time, and also a reset time. And in the protection settings itself, you will find the switching sequence for the recloser. So the 4 sections, we only have a look to the first section. We offer at the moment 2 cycles, and this is the disconnection time, and we want to work with my I bigger, which has a time of 30 milliseconds, and at the end, the final switch off will also work with this I bigger. Okay. Now we simulate the fault. We calculate, for instance, a 3-phase short circuit. Say OK. And then we will see a lot of time steps differently than before. Also the colors, you see Now it's orange. This we did not have before, so we added different states. Before, for instance, if it's something is active or switched off or conditionally tripped or before the reclosing, so we will see we have this orange conditionally tripped because of the first cycle, and you will also see the reclosing later on. Okay, so at the first moment you see after the fault happened, we have 30 milliseconds from the bigger criteria, and after 20 milliseconds further there was a trip that was the switch off time. In the next cycle you see a reclosing phase. We have a waiting time for that, a delay of 100 milliseconds. With the other switch on and off times, you will see after 170 milliseconds, the closer will reclose. Then the next step, you see, that's the second cycle after 30 milliseconds again, or 200 milliseconds in total. It will trip again, switch off time 0.02 seconds. That means 220 milliseconds to disconnect. Then the next loop, recloser time again with 100 milliseconds delay. Then the final opening, because even then I have my short circuit current at that location and cannot be completely tripped, and therefore this is now red. That's the final simulation, and in the next step you see no current again from this side, and therefore disconnection. Okay, then we go back. We not only added the recloses, but also other very important topics. One we already have seen. We have now individual switching times for each protection device. We then added multiple current transformers for overcurrent and distance protection devices. That means you have now up to four different current transformers and also voltage transformer. That means you can now add specific currents or subtract specific currents to get some at the location of the protection device, and then trip or decide about tripping at that position. You also have multiple differential protection areas per protection device now. That means you can save differential protection devices. For instance, if you have a transformer, the transformer itself may not have, but all the outgoing feeders may have differential protection, and this can work still. Then you can build a summary of measure points for differential protection, as I said already. We also offer additional delay time for protection, overcurrent time protection devices, and we have a sensitive ground fault detection for protection also ready, a specific method for the simulation. So we can, when you select in the settings the direction of determination as isolated in this case. One of the features which was also linked to the new version was that we have a new option for verifying the good connection of DER. You know, we have the BDEW standard for the German specifically, but also for the European. Check if you can link a DER to the system, and we also offer a specific method for the Australian user group that is based on the NER standard. And now in the US there was a new standard coming out 2018, the IEEE 1547, and therefore we linked also this standard to Sincal, that you can directly add the element, check if it's possible to link the DR according to this standard. So we check the different connection rules, and I guess we should also directly go into the software. we have a small network again to verify if it's possible to link to the system or not. So differently to the other simulation methods, you will see that you have to define a PCC, point of coupling, for the DR. In general, this will be the position where it is linked to the public network, for instance, across this transformer. So in this case, this bus bar will get a PCC configuration. At this PCC configuration, you will decide if you want to give only the demand load current or also the ratio from the short circuit. At the moment, we decided only for the demand load current. Maybe it's 250 amps. Distortion limits you can also give. At the moment, we did not define it here. So next step is that you select the element you want to check, and directly at this element, at the context menu, you will find a calculation at the element and the verify connection condition. So when we click on that, we get to a wizard, and in the wizard you will see, okay, first of all, this is a page where you can give information about the testing case. The second is the technical data. I want to calculate according to the IEEE 1547, the network type, medium voltage, low voltage, then the maximum active power and the power factor. If it's a supplier, then you can decide if you want to consider with transformers or with function groups, and then for the fault right through, different characteristics, for instance. The location for the RPA can be selected. The next is the flicker data. So there are the 12 values in for the first 2 hours, or for 2 hours you can have in a 10-minute step the flicker coefficient you want to fit in, and therefore you can define it here. And then for the harmonic data, when you activate it, you can have the distortion limits according to the TRD. By the way, this standard is also based on current distortions, not only on voltage distortions. Then you give the fundamental current, and then the RMS current for all frequencies and the direct current. And when you tick create documentation here, then while you simulate, you will also get more information. So it runs now through load flow, it runs through short circuit, harmonics, and then creates a documentation, which means we have a Word template in the background, and it fills the results of the calculation directly into the Word template that you can then later on handle this script or this Word document over to a to the utility or to a regulator, then that it can be allowed to link this DR to the network or not. The first view is that I can have a quick view about, okay, this is my project, these are my technical data, at which node I link it to the system, what is the control characteristics for the fault right through, and at the end I see a quick overview about the state. The utilization was fine, slow voltage changes were okay, fast voltage changes also. Flicker evaluation also, but we have an issue with the harmonics. That could be, so we can have now a look into the documentation. We can go into show documentation, which opens the Word template with the results. And when I have a look into it, I see, okay, the first page is just information, and then I get a content page. You see up to 12 pages at the moment with all the information about the checks. I get a summary, So the point of common coupling is mentioned here, according to which standards I did the checks, which investigation I did, and if they are okay or not passed, and then the details of the machine, the details about the utilization of the transformers and lines, then the different performance for the different power factor. That means the voltage hub is within a limit, so it's not very high in this case. And I also will get information about my flicker, which are okay, and about my harmonics, which may be okay in parts. And of course I get then some information about what is the base of the simulation. And this now I can directly hand over to a regulator to get the permission to link to the system. Okay, this I don't want to store, but I turn back to the slides, at least to one of the last slides. So as in any version, we care about the calculation speed. Every time we will have optimization in the speed, and this year we did it the same, and we do it at different locations. One location is of course the data structure, where we want to optimize that we handle the data in the right way and that we do not have to have too much loops and too much structures in this. Then we have algorithms which can be efficient, get more efficient. So we change something into the algorithms, or we optimize the way to find things there. What we also did in this version, we added the MKL library for the simulation in load flow, but also in short circuit and in harmonic calculation. Specifically, this is good if you want to solve the sparse admittance matrix. That's then in many cases much quicker. And when we get back to the beginning of this presentation, to work with SQLite is even up to 50% time saving against MS Access. So on average, we believe that we got a speed improvement up to 2 to 5 times. And this is really something you will feel with a new version, for sure. So this is a quick overview about the important features of the version 15.0. For more details, please also refer to the release notes. And thank you very much for your attention.
All right, thank you, Ulrike. We're just about to jump into our questions and answers here. Ulrike, would you mind moving to the next slide?
Sorry,
Would you mind moving to the next slide with the online
slide?
42? Perfect.
Sorry.
Oh, that's all right. All right, so before we get started with questions and answers, just a reminder, if you do have questions, please enter them using the question feature on the right-hand side of the screen. I did want to give you an update. We recently expanded our PSS online store, and Ulrike, I'm still seeing the older slide. That's all right. So we recently expanded our PSS online store with the option to purchase 6-month and yearly Sincal packages. So if you're in the need for that, please visit our online store. It provides you with a streamlined purchasing process, and you also get M&S for the full subscription term. Then, if you would like to continue your journey with us today, I did have a couple links on the next slide where you're able to do that. One link in particular that I would like to point out is the PSS webinar archive. A recording of this webinar will be available on the archive. So I know that's a fairly long link, but if you go to the handouts section in the GoToWebinar control panel, you're able to download the presentation slides, which do include that link. All right, so without further ado, let's kick off into our questions and answers. So the first question is, during sequential fault clearing, the coordination time interval, CTI, between backup and the primary protection devices changes dynamically due to the changes in topology and therefore fault currents. Does Sincal track the changes or the changing CTI and report it?
First of all, I have to read through. Sorry, Ashok. So Sincal calculates in each step again the short circuit, and with this again goes into protection devices and checks the tripping times. Is this what you mean? Otherwise, we can get in contact again and have a look to it. So I guess yes, we do it, but maybe I did not understand it quite well.
All right, thanks, Ulrike. The next question is, can you please indicate what types of recloser curves does Sincal library support? Typical for the US market are the curves that are identified by numbers such as 101, 103, 104, 117, and so on. Are these curves supported in Sincal out of the box?
We have reclosers defined, but not a large number. But every user can define the curves for the reclosers as all others overcome time protection. As a normal curve with XY coordinates, and define that and add it to the reclosers.
All right, thank you. Next question is, we are currently using version 12.5. I would like to confirm that we can apply filter on multiple parameters for nodes/network elements using and/or functions.
For the in 12.5, the new tabular view is not available, and therefore you cannot work in this way. So you have to go to 15.0 to use the specific features of this new tabular view linked to the network browser.
All right, the next question is, does the fault location technique use any published fault location algorithms? Or is it based on a search through the network trying to match the measurements to those produced by the fault application?
Okay, so what we do, we calculate a short circuit sweep through the network, calculating the network impedances, starting from the measurement point into the system, and find out where the network impedance, the complete network impedance with all the impedances in the background, links to the measured values. And that is the method we do. So running a sweep, a short-circuit sweep through the network, finding the locations in the system, and then matching that together with the other simulations from other measurement points. So based on the real calculation in the system.
Okay, the next question is, in the reclosing sequence shown, it appears that I was used...
bigger here.
Yes, okay, thank you. I bigga was used for each tripping action. Can I use I bigga for the first tripping action, but use IP for the 3 remaining tripping actions? Sometimes...
Yes.
Sometimes, it's a two-part question. Sometimes I might want to use one type of IP for the first trip, but use a different, slower IP for the remaining 3 trips.
Yes, you can. I said we have different sequences and different cycles. So we can have up to 4 different sequences, maybe I bigger, and then change to IP. And this we can do for up to 4 different steps, and each step can have different cycles. Yes, correct, completely correct.
Okay, great. Excuse me. The next question is, do we have all examples included in the project library, or were they just on your folder? For example, the example of the recloser.
The recloser is not in the project library, but I can give this example on a drive or send it to you if you want to have it. Not a problem. So example L1, example L2 is on the drive, recloser not, and also the testing system for the IEEE 1547 also not.
All right, so with that said, Ulrike will follow up with you after the webinar to send those. And the next question is Sincal 15, version 15, have a remote connection feature? This is very much required to handle the big distribution network. Idea is to connect 2 networks on separate pages.
At the moment, I do not exactly understand what you mean. So we have the option of include networks. That means we have 2 different networks in 2 different databases and link them together only when you need it temporarily. I'm not sure if this is meant is what you talk about, because this is available already a long time, but maybe it's the answer to what you want to have. So connect 2 networks on different pages. What is page? Is this a network project? Is it a project, or it's just on the screen? So different views of the same network. This is also possible side by side. As you have seen, I could split the view on the screen to 2 different pages.
All right, so it looks like the person who asked that question just clarified, and they said the big network which cannot be drawn on A0 size.
Okay, that means you want to print it out. Of course, you can have frames you can print separately. You don't have to print the network complete as one. You can have different frames and then print all the frames in one run, but on different pages.
All right, great. Next question is there a manual for creation of overcurrent protection devices with detailed illustrations? The information about the commands is hard to find and analyze. Would be thankful to get any extra information regarding the overcurrent protection creation in Sincal.
There is a specific section in Sincal where you can, where it's described how you create the template for the protection devices. I guess you mean that. That means you, from the scratch, if you have a new protection device, how you can get to a template in the local database. That is possible. We normally recommend that you start with looking for an a protection device which is nearly what you want to have, copy that into the local database, and then make changes in this database. But there's a description for that, yes.
Now, Ulrike, we did do the 2 protection webinars last year. Would that be covered in one of those webinars as well?
One of the slides, yes, I explained how it is done. You're right, Danelle, yes.
Okay, and just for everyone's awareness, those 2 recorded protection webinars are on the webinar archive here. All right, so then we'll go off to our next question. Does Sincal help into detecting bus overloads in terms of continuous current rating?
Does Sincal help in detecting bus overload? That is something we could do when we have the SPY implemented. That means we read continuously data from the field, measurements, and with this then find out if, for instance, if you have a short circuit or a load flow, if you are overloading elements, and that includes also the bus currents. This is something we added some versions before, that you have also current limits at the buses, yes. But if you want to do this continuously, it is a project to set up a linkage to the MDM system to get the readings from the field.
All right, and then our last question for today, is there any interface to other engineering software like MATLAB, for example, in order to hand over machine parameters to Sincal or Netamac?
What you can do, if you have a controller modeled in MATLAB Simulink, you can directly embed that in the dynamic simulation within Sincal. That means we have a wrapper around the MATLAB Simulink which grabs the data from MATLAB Simulink and brings it into our controllers. But then it has to fit into the IEEE defined standard. I guess it's Annex F of an IEEE standard, where it's defined how this MATLAB Simulink has to be set up. Yes, we can do that.
All right. Thank you, Ulrike, and thank you everyone for joining us today. That's all the questions we'll go over for now. I did see there's maybe one more question on there, so we'll get back to you in a follow-up email after the webinar. And Ulrike, if you wanted to say any final words, I'll hand it over to you.
Oh, no, I thank you very much for the interest, and I hope you got some information out of this webinar. Thanks.